All right, so I'd like to start by going over the syllabus. Looks like we have a bit of a black zone at the right side of the screen. All right, let me know if that's covering up any important information at any point, and I'll stop and reformat it. But I posted the syllabus and course calendar on Blackboard, so you should be able to see that. If you don't have access to the Blackboard site yet, come and talk to me after class today. Let's see here. All right, so this is Electromagnetics, fall 2017, and the topics in this course is the fundamentals of electromagnetic engineering, static and magnetic fields using vector analysis, fields of steady currents. We'll talk about Maxwell's equations, and we'll do a lot of problem solving and boundary value problems. We'll talk about the principles of plane waves and transmission lines and radiation. We've sometimes gotten to in the past, but usually we don't get to that. So in terms of the learning objectives, the first thing that we'll start off with is basic problems in vector algebra, dot product, cross product, gradient, curl, and divergence. How many of you remember that? I heard a few groans. Sort of. Okay. Well, that's so these concepts are essential in electromagnetics. Integration and vector algebra are essential. So, in a way, if you didn't like it the first time, there's a good chance you may end up liking it more the second time if it's applied to a certain topic. Or sometimes, the second time you look at something, you end up learning it a lot better. So in a way, this class will be a way for you to learn those essential mathematical concepts better. And by having a lot of visual illustration of those concepts, it may help in having a deeper understanding. It may be that your second time encountering these things will be just as miserable as the first. That's also possible, but I'm here to help you learn those concepts. They will be very important in this class. If you enjoyed them the first time, you'll enjoy them even more the second time when you see them applied to electromagnetics problems. Learning objective number 2 is going to be learning to understand and analyze electrostatic fields and currents. Number 3 is understanding and analyzing static magnetic fields and currents. And there is a number 4 here. I think I may have a different version of the syllabus here. The number 4 you'll see. I will post it up there. It's using computational tools, MATLAB, and a tool called COMSOL to simulate, to numerically solve electromagnetics problems. One of the things that we want to do in our programs at the undergraduate and graduate level is to familiarize you all with tools, not just doing problems out of a book, but knowing the tools that practicing engineers would use. And so for this particular class, we're going to use MATLAB to do some vector math, and we are going to be using COMSOL to simulate electrostatic problems. All right, and it's a really nice tool for you to learn how to use. Time permitting, we will get into time-varying magnetic fields and Maxwell's equations. And if we get even beyond that, we will get to plane wave propagation and radiation. I think most likely it will be these first 4 topics that I just mentioned. So in terms of ABET outcome coverage, this is something that, some of you have heard about ABET. It's an accreditation. Wayne State is an ABET accredited program. So in order to keep that accreditation, they have certain focal points or certain goals that they want all undergraduates to know. And you'll notice that these things are very general. They're the topics listed in italics here. And so, the ABET goals for this particular class include the ability to apply knowledge of mathematics and science and engineering. Because this class is very heavy on math and applying principles of math into electromagnetics, which is an engineering concept. So You will definitely be using a lot of math in this course. You'll be using a lot of physics too. Ability to use the techniques and skills in modern engineering tools. I mentioned that one of the things I want you all to learn is using MATLAB to perform vector and matrix calculations and plotting vector fields. I would like you all to also learn a tool called COMSOL for doing finite element simulations of electric fields. And it sounds complicated, but the way that we're going to do it this term, we're not going to get into all the details of finite element simulation. I'm just going to show you how to use this tool to solve electrostatic problems. Because you learn the theory, you learn how to solve basic problems by hand, but you only learn how to do the most basic problems. When you have more real-life situations, like real-life geometries, then you will need to use numerical solvers to figure out the electric fields and voltages and so on. Only in the simplest of cases can you actually solve them by a basic integral, which you'll be doing in this class. Good tool to learn. The broad education to understand the impact of engineering solutions in a global environmental context. This is the fundamental topic, so it applies to all sorts of electrical and electronic devices and phenomena. And the ability to identify, formulate, and solve engineering problems. So in this course, probably like your other courses, maybe even more so than other courses, you'll be doing a lot of problem solving. A lot of solving for electrostatic fields, a lot of vector calculus, a lot of vector math, and we will go over it in a way that is doable for you. But it is something that builds on vector calculus. So we'll spend time to go over that in the beginning and make sure that you keep up with it and that you learn it well, because you will need it for the second half of the course. So it doesn't seem like I have the most, not quite sure what happened here with the syllabus. It seems like I have an older version of the syllabus that's on my laptop. I have a synchronization between my work laptop and my work desktop, so it seems like that I have an older version here. So let me just mention just by voice that the course textbook is not going to be this David Cheng Fundamentals of Engineering Electromagnetics. It's going to be the book that I have here, Fundamentals of Applied Electromagnetics by Ulubi. So a couple of years ago, we switched back to this book, or we switched to this book, I should say. This is actually a similar book as what I used when I was an undergraduate. And one of the nice things about this book is that it's actually quite concise. Some books get very wordy. This really distills down the basic and fundamental concepts. Another nice thing about it is that it is you can get inexpensive versions of this online. The paperback version of this might run you $60 or so. Maybe even less if you can get them used. They're less? 35. Okay, great. It's not new. Yeah, there's a paperback international edition of this book that's relatively inexpensive. So there's multiple editions. I'm actually holding an older edition. The most recent version is the 7th edition. I wouldn't worry too much about which version. The content, the fundamental content doesn't change very much, and a lot of the class will be based on my notes. So the book will be a reference for you to go to when you don't understand something that's in the notes. But this class will be based on the textbook. The notes will be based on the textbook. Okay. So I considering that it's only like $35, I think it's a great idea to have this as a reference. I've really appreciated this book. It's a really, really nice reference. You used it throughout grad school. All right. So uh, in terms of the modules that we're going to cover, the one that we're going to cover today, depending on how much time we have, is in the introduction. I will introduce concepts. I should say the introduction section is going to be more or less motivation for electromagnetics. I'll show you some of the applications of electromagnetics in the real world and emerging topics in electromagnetics, some of the devices that we use every day that incorporate electromagnetic devices in there. So it's a way for you to get introduced to the field and a motivation for studying the field. I like to do that with most of my classes. Next Monday is Labor Day, so we will not be having class then. We will jump into vector calculus starting next Wednesday. All right, we're going to dive right into the math. We will be going over things like the how to add vectors, how to do the dot product and the cross product, how to do divergence, gradient, and curl, these essential operators that are used in electromagnetics, how to do the vector product, how to do the triple product, the Laplacian operator. The reason we go over these vector operations is because they are used to solve problems in electromagnetics. Okay, for those of you who've taken physics classes before, you end up using those vector concepts quite a bit. So if you have time over Labor Day, while you're up in your cabin trying to relax, just kidding, you can get a Shams outline on Shams review of vector calculus or Shams review of multivariable calculus. So being able to do your like double and triple integrals and being able to do vector math are probably two skills to brush up on. We will be going over them, but since we don't want to spend the entire class period, we don't want to spend the entire semester on it, we will be going relatively quickly so that we have time to get into the electromagnetics concepts. Okay. There are a lot of resources on vector math and multivariable calculus. No problem. So there, you could use any of these, like a Shams outline. One of my favorites is Khan Academy. Khan Academy goes from kindergarten all the way up to advanced concepts that you learn in graduate school. And I used it just last week to brush up on some statistical methods that are used in population statistics. So it's a great resource. There's a lot of other resources like that online. Sometimes it's just a matter of knowing where to look. Wikipedia is also, it turns out, it's very good explanations on there. So as we go through it, I will point you to certain references, but if you'd like to get started, those are some of the places that you can look at right now in the next week or so. After we do vector analysis, I will probably do one or maybe two lectures on fundamental concepts in electromagnetics. Things like, this will be a physics-oriented lecture, right? It'll be just about attraction between two charges. We'll talk about Coulomb's law, the Lorentz force, the Biot-Savart law, some of these very fundamental things about electric fields. We won't be going into any of the details of it. We'll save the details for later. But this is just an introduction to the physics of electromagnetics. Next, we will talk about electrostatics. And this is going to be the first of two major units. So Module 4, electrostatics covers many different topics. One of the things we'll be looking at is charge distributions. So if you have a set of charges, what is the electric field that's coming out of that charge? We'll talk about Coulomb's law. We'll talk about vector electrostatic potentials. So when you have a voltage, an electrostatic potential, how do you calculate what that potential is? We'll talk about things like electrostatic fields and electromagnetic work. So if you take two charges that are of same charge, two positive charges, they repel each other, right? But if you bring them together, if you push them together, it takes some force to push them together, right? So you're putting work into the system. So if you have two like charges that are next to each other, that system stores energy. So we'll talk about this concept of electrostatic work or electromagnetics work and how that relates to energy and so on. We'll talk about things like capacitance. Dielectric materials have a property called capacitance. Then conductive materials have a property called resistance. So we'll look at the origin of capacitance and resistance. That's a very important topic in electrostatics. Then we'll move on to magnetostatics. So we'll talk about electric fields first, Module 4, and then in Module 5 we talk about magnetic fields. So just like there's some fundamental laws like Coulomb's law, the repulsion of like charges, in magnetics there's also fundamentals laws like the Biot-Savart law, which describes the magnetic field that is generated whenever you have current going through a wire. We'll solve a lot of problems related to the Biot-Savart law, the calculating magnetic fields. We'll also talk about the Lorentz force. So that's an electromagnetic force. If you have a charged particle moving through a magnetic field, the magnetic field will end up deflecting the particle. This is the type of force that's used in Hall effect sensors for sensing magnetic fields. It's also used in these big hadron colliders. You know, you've heard about the 2-mile-long accelerator in Switzerland, in Bern, in CERN, I think. They use things like electrostatic acceleration. They also use the Lorentz force to deflect particles one way or another. So we'll learn about that. In magnetostatics, we'll learn about inductance. All right, does anyone know what inductance is? Or can anyone define it? Close. Yeah, inductance is induced current from a magnetic field. That's one way of describing it. It is also it goes the other way too. If you have current, then you generate a magnetic field. And that coupling between those two has to do with the inductance of an object. So we will talk about what inductance is and how it can be used in solenoids. So solenoids, you know, your door locks, when you press the power locks, there are solenoids that cause the door lock to go up and down. It's a magnetic force that does that. In the opposite direction, when you go from magnetic field to a current, that is an example of where you can generate power. You can generate current from a turbine. Okay, so I'm going over these topics very generally right now. We will get into the details of it later. I'm just giving you a flavor for the type of topics that we will cover. So that's at magnetostatics, and then we'll have a second exam, Thanksgiving break, and after Thanksgiving break, time permitting, we'll get into time-varying fields. So we'll learn about these things called the Maxwell equations. Have any of you heard about the Maxwell equations before? Okay. Well, one of the things about the Maxwell equations is that if you're dealing with statics, meaning fields that are not time-varying, then it turns out that electric fields and magnetic fields are decoupled from each other. So you can solve what your electrostatic fields are, you can solve what your magnetic fields are, and they don't couple into each other. You can solve them independently. When you have time-varying fields, the electric fields and magnetic fields are actually become coupled to each other. They're related to one another. So then you have to do you have to go back to Maxwell's equations and then understand. You have to be able to actually solve all 4 of those equations to understand time-varying fields or dynamic fields. So we'll talk about some of the properties of time-varying fields. That will take us to the end of the semester. We'll do a review and catch up probably the last day of class on December 11th. And our final exam is scheduled for December 13th. So relatively early. You'll be done with this class before mid-December. So you'll have a long Christmas break. Any questions so far about the calendar? All right. Let's jump back to the syllabus then. Attendance policy. I do require attendance in the class, and the reason I do that is because I think that if you are spending such a large amount of money on tuition, I think, what is it? Is it like several $100s per credit hour? Yeah. So $400 per credit hour. This is a 4 credit hour class. You're spending $1,600. Right. So it comes out to something like maybe $100 per class that you're paying. Something, something close. So education's expensive, and I think that when you're an undergraduate and you're taking so many different classes, you kind of forget how much you're actually paying to be sitting here. So when I think of it, it makes me think that, okay, well, we better, if everyone is paying this amount of money to be here and to be learning from the person teaching the class, then I better do a very good job. And so I feel that way, and I also feel that learning is an enterprise, meaning I want to have your involvement too. The way I like to run my classes, yeah, I will spend a lot of time lecturing up here, but I want it to be as much of a conversation as possible. So if there's things that you're not sure about, I'd like you to raise your hand, and we'll go over things as many times as you need. There's no such thing as a dumb question in my class. I want to make sure that you understand the concepts well, and I would rather that you understand a concept well rather than we just get through all the material and you don't understand it well. Right? So I want to make it as much of a conversation as possible. I've noticed that in the past, in some classes, it happens very well. In some classes, the students are more shy. So I want to kind of set the tone right from the beginning. Like, just feel free to interrupt me, and if you have questions, let's all figure it out together. So for that, I need your participation in the class. So I need your attendance in the class. If you have personal, medical, professional reasons, like I allow like up to 3 absences for that, but just let me know if you're planning to miss the class. Okay, I'm not going to be a tyrant about it, but I would like to know, like, if you're planning to miss a class, it's good if you let me know in advance. The exam dates that we have listed in the course calendar here. On these dates, I definitely would like you all to make a commitment to be here on those dates, block those dates off in your calendar, because I generally do not give makeup exams, so I'd like you to make sure that you're here on those exam dates. We will have an exam in October 11th and November 15th, and the final exam will be December 13th. Okay, and those exams will generally be the entire class period. The final will be mostly on the last part of the class, but as is the case with the other class I teach as well, this is very much the topics itself are very cumulative. If you don't know vector math, you won't be able to do the magnetostatics material. So it's important that you know that you will have to know all the class material and keep up to date with it as we go. The grading policy, again, I apologize. I don't know what happened here. This is my old grading policy. 20% quizzes, 45% two in the midterms. Let me just, just so we're clear here, I'll update the new grading policy on there, but the two midterms are going to be 20% each. All right, so for a total of 40%, final exam is going to be 30%, and there's going to be 15% on quizzes, 10% on a lab assignment. All right. So let me make sure that adds up. All right, 40%, 70%, 80, 95, 5. Right. All right. So what are these different things? Quizzes. The quizzes will have them scattered throughout the semester. Some of the quizzes may be done here. If I get some of these Blackboard things working, I might do some quizzes online as well. Right? You could do at home. 10% is going to be a lab assignment. So I mentioned that this class is you're going to learn MATLAB, doing vector math with MATLAB, and then learning how to do electrostatic simulations in COMSOL. So we will have probably two assignments where you're asked to go and do a few things in MATLAB and COMSOL, do some simulations and computations, just so you understand how to use the tools. So MATLAB, how many of you have MATLAB installed on your laptops already? All of you. Is anyone doesn't yet? Okay. I believe if you go to Connect Services, they can help you get that installed. They have a virtual, they have something called vTools now that allows you to virtually install it, so you don't have to actually go there in person and do it. Is that right? Like some of you, I saw you were nodding. You use the vTools? Okay. You have to have an internet connection in order to do that. You're accessing it virtually. All right, so that means you have to have good Wi-Fi to do that. It's free. Yeah. Now COMSOL, I think that our license restriction says that you actually have to go and use COMSOL on one of the lab PCs. So you may actually have to go to the engineering computer lab to use COMSOL. We'll probably have a class session where I actually go in there with you and I show you how to use the tool. Okay. So I think that'll be interesting. The two midterms, each 20% of your grade, and the final exam is 30%. So you can see that the tests really are worth the large chunk of your grade. Okay. So you want to make sure that you understand the material well. The quizzes, and I will also have homeworks that won't be graded, but the purpose of those things are really just so you understand the material for the exams. And then 5% will be attendance and participation. How many of you have iClickers? Right? They have a remote, and they also have the app now, smartphone app. Yeah, so I played around with that a little bit in my class last term. I had some questions, and you can answer them through your phone. So we may be doing that again this semester. So just keep that in mind. If you don't have the clicker, I think you can pay $15 for a 6-month access to. You can get the smartphone app for free, and then you have to have a subscription, which is I think $15 for 6 months, so you can use that for your classes. So I'll give you more information about that in the future. This is the grading scale, and so it says subject to change because I usually do curve the class a little bit at the end of the semester. These scores here, if you get a certain percentage in this class, if your average is let's say an 80, well, you're guaranteed a B. Right? If you get a certain percentage, you're guaranteed that grade. And if the curve helps you, you might end up getting bumped up like one letter grade. Exactly. Yeah, exactly. I do that based on where the class averages are in relation to previous years. Right. It's, for example, if I end up giving a very difficult test and the averages are lower, I usually will, be more lenient with that at the end of the semester. In the past, what usually happens is that your grade may go up by a third of a letter grade, meaning like you may go from a B to a B plus, something like that. Okay, so the policy for cheating. This is probably something that you've obviously covered in your other courses as well. Cheating is something that I feel, very strongly about. If I see that you have cheated, so cheating is defined as intentionally using, attempting to use, intentionally providing, or attempting to provide unauthorized materials, information, or assistance in an academic exercise. In some cases, I will allow you to work with others. Like, when you're doing homeworks, you're more than welcome to work with your classmates. But ultimately, I want you to do the work on your own. You can discuss with your classmates how to solve the problem, but ultimately, I want you to solve the problem on your own. On tests and quizzes, you're obviously completely on your own. Now, we'll have like the standard policies, like, in exams, I expect you all to sit, 2 desks away from one another, no cell phones allowed, no electronic devices allowed. And, I know I've heard from students that there are all sorts of tools available, ways to get information and tutoring online. I don't mind if you get help for homeworks and things like that, or if you need help in understanding a topic, but I will be very strict about this. If I see or if I catch anyone using any of those online tools for tests, I will give you a 0 on that exam, and I most likely give you a 0 in the class. Okay, I will not tolerate any of that sort of stuff. Okay, so I'm just letting you know beforehand, because I hate being the bad guy. I've done that before, but I have 0 tolerance for this kind of thing. Okay, so just want to make you all aware of that from the beginning. There's some information about the academic integrity policy at Wayne State. You can read about that online. Most of you are familiar with it already. So in Blackboard, we'll be using Blackboard for this course. We go to it right now. Show you. We have the syllabus is on there, course calendar is on there. I will be posting lecture notes. Oh, let me. Yeah, so lecture notes are online. I will also post links to YouTube for our lecture recordings, so you have those as well. And homeworks and things like that will be posted as well. Usual stuff. Feedback, dropping and withdrawing from a class. I do like to get feedback from students whenever, instead of waiting until the end of the semester, let me know beforehand. If you're concerned that we're going too fast in this class, you're concerned with some issue in the class, it's better that you let me know as soon as you can, rather than waiting until the end of the semester on the course evaluations, because then I can't make the change and improve the class for you. So please let me know. beforehand. If you are having trouble with anything in the class, please let me know. Any other issues, I'm here to help you. Dropping and withdrawing and these educational accessibility services, these are all typical stuff that you see in all your classes. The main thing I want to point out, which some of you know already, is beginning the 5th week of the class, students are no longer allowed to drop the class but have to withdraw. Okay, and withdrawing, as you know, is different than just from being able to drop the class. Okay, so if you decide that you're going to drop the class, make sure you do it before then so you don't get a W on your transcript. Questions? Yes. Yes. How does vector calculus differ from tensor calculus? Well, tensors are matrices, right? So vector calculus will be, I would say, less complicated than tensor calculus. It's a subset of it. Yeah. Vectors are, they're columns. They're columns or rows. And tensors are matrices. Okay, so what other material did I have here? It's right now it is 1:30. So we will be ending class at 9:10. Right, so this class will go until 9:10. Let's take some time now and go through the rest of the introductions, and then we'll finish up. Yes. Office hours will be from 3 to 5 p.m. on Mondays and Wednesdays in my office. Yes, my office number is on. It will be on the syllabus. I'll update it. I think I had a little goof up here. 3133 engineering. So would you like to introduce yourself? All right. Hmm. Let me ask you: Is this? It's changed then. There was a yes. Okay. Thanks for that clarification. Yeah, it used to be required for everybody, but then I think it was changed to be. I gotcha. Okay, thanks for that clarification. So now, all right. Mhm. Oh, fantastic. Excellent. Very interesting experience, I'm sure. Great. Jeremy, do you want to go next? Since you were mentioned. Mhm. Your stories corroborate. That's good. All right. Thank you, Jeremy. And let's see. Let's go. Sajjad. Sajjad.
I graduated in year my bachelor's and I'm going into electrical engineering, and then I do plan on getting my master's too after that. And I'm taking this course because it was required. And the last place I traveled was Atlanta for work.
Where do you work?
And it's Sprint.
At work?
Sprint.
Sprint. Oh, that's great. Well, Sprint's a wireless company. It's oh, I had Sprint for a long time. I had Sprint all through grad school. I never had a problem with it. Okay. And well, what are you hoping to get out of the class? Mm-hmm. Okay, great. Welcome.
I graduate next semester. I'm an electrical engineer. I'm trying to be an international engineer where I work with different groups, specializing in sensors.
Oh, excellent.
And I'm planning on retiring in 15 years to Ohio, Cedar Point, Cal kicking back, having fun.
So sensors, the electromagnetics obviously plays a very important role in sensors. I'll mention a few things in the upcoming slides that I'm going to go over today. Good.
Senior in electrical engineering, got a year left. Career plans, since I've worked where I can travel, choir class, interested in learning about more the nature of EM waves.
Mm-hmm.
The last place I went to, Bus to Chicago, and back.
A megabus? Yeah. Great. All right. Well, welcome, Noah. Nice to see a familiar face. That works, yeah.
And I've been working with B2X and GNSS.
B2X? What is B2X? Oh, V2X. Gotcha. All right. Oh, excellent. Did you go up to Half Dome? A lot of waterfalls there. Yeah. Amazing place. Great. And last but not least.
My name is Charles Hamilton. I'm a senior electrical engineer. Graduating in May. I took this class because I had a good teacher, and I wanted to have for electronics too, but
Oh. Oh, good answer. Good answer.
I currently work at Sumitomo Electrical Wiring Systems. It'll be a year since I've been there on Tuesday next week. And currently right now, do work on Cherokee wire harnesses. Like I've done work on the liftgate harness, some of their the doors, the right door, the driver passenger doors. And the last place I've traveled to is Cedar Point with my girlfriend over the summer.
I think you the things, the automotive wiring. There's a lot of like EMC related topics in that, so I think you'll find that interesting. Great. Well, all right. Welcome everyone. So it's good to see some familiar faces and a lot of new faces. So as we go along the semester, please forgive me if it takes a little bit of time to learn your names. But whenever you all ask questions, please remind me what your names are. And over a few weeks, I will eventually learn them. We have 20 students in this class, so it'll be easier for me to learn everybody's names than when we have these huge classes of 45, 50 students. So I'll do my best. But bear with me if I don't get it quickly. Okay. There we go. All right. So this first module is an introductory module just to give you a motivation. This is where you can just sort of sit back and relax and sort of learn about the fields. I'm not going to test you on the topics in this module, right? It's more of just a motivation and get the discussion going. So the things that we're going to talk about in this class, already mentioned some fundamental concepts in electromagnetics, those physics concepts. We're going to spend some time reviewing vector calculus. Electrostatics and magnetostatics are going to be the main content of this course. And if we have time, we'll get into time-varying fields and wave propagation. So in terms of study suggestions, I have similar study suggestions for my other class, but I think it's particularly important for electromagnetics to visualize and categorize and do a lot of practice and review. So visualizing means like getting a qualitative picture of what's going on. You'll find that this class is very math heavy, and if you immediately just start solving the equations, you may miss out on the intuitive concepts. I think it's very important as engineers for us to get intuition about physical phenomena and how they work. And if you have a good physical intuition, then when you plug the numbers into the equations or you solve an integral and you find the result, then you'll be able to sort of make sense of the result. Okay? Building that intuition is extremely important. Visualizing is also turns out to be very important for vector calculus and multidimensional calculus. Right, being able to picture which directions the fields are going, being able to imagine a three-dimensional surface that you're going to do an integral over when we get into the divergence theorem. So that type of three-dimensional visualization is important. I want to make sure that you know how to do that. Categorizing, there's a lot of concepts in this class. I wouldn't say it's an overwhelming number of concepts, but enough where you should make sure you kind of like organize it. When you take notes, just write down notes on there. Don't just look at the PowerPoint slides. I know it's very tempting since I'm posting the notes online and posting them on Blackboard that it's tempting to just not actually spend time writing and figuring things out on your own. You will remember and learn the most if you actually write things down and sort of take notes as we go along in the lecture. So one thing you might do is you can keep a copy of printout of the notes on the side, but then also have your pencil out and scratch notes on the slides themselves or on a separate piece of paper. That's what I would suggest. If you print the slides out, one slide per page, you can jot a lot of notes in the margins and on the sides and in the white space. Practicing, this is one of those classes, there's a lot of problem solving in this class, and it's not plug and chug type things. I would say in the devices class in 4570, there's a lot of, you can use the equations that I gave you and solve those. In this class, it's a lot of more conceptual problem solving where you're doing a lot of mathematics from a lot of integrals, and it's not just plugging numbers in. So practicing these problems quite a bit is important. I'll give you a lot of practice problems to do. And reviewing, of course, for the exams. Okay, plan on spending maybe 12 to 16 hours a week for this class. It's a 4 credit hour course, so you multiply the number of credit hours by about 4 hours per week. That's how much time you should expect to spend on this course. About my teaching style, I mentioned I want your participation and I like it to be as informal as possible. Obviously, I will spend a lot of time just speaking to you, but I would like to make it as much of a conversation as possible. I feel very strongly about having no dumb questions. So if you are thinking about something and it doesn't make sense, chances are other people in the class are thinking the same thing. And I may not realize that because I'm busy, moving on to the next concept. Or maybe I'm not seeing it the same way you are for the first time. So when you're not sure about something, please ask. Don't feel embarrassed. And come to my office hours if there's topics I can help you with. You can ask me questions after class, since it's the last class of the night. If you're not feeling very tired by the end of the class, you can always ask me questions afterwards. We can go over things. I have no problem doing that. All right, so that's about the class. Now let's spend a little bit of time in the last 20, 25 minutes or so going over some things about electromagnetics. So again, this is to help motivate you about learning this topic. And so we'll mention a lot of different areas where electromagnetics are applied to engineering or just applied to the real world. This is a picture from Ulaby's book, Fundamentals of Applied Electromagnetics. It talks about a few of the important areas where electromagnetics plays a very fundamental role. Things like radio and telecommunications, obviously, like, you learn about wave propagation. Electromagnetic waves are used to communicate satellites. In wireless communications, your cell phones are picking up very, very weak electromagnetic signals that are radiated from your cell phone towers. And it's amazing that this small device with an antenna that's about this big can pick up those small signals, amplify them. That's the electronics part of it, but just the fact that there are electromagnetic waves that are radiating from cell towers and satellites and are coming to your phone. And everybody has a different information going in there. It's pretty mind-boggling. It's pretty awesome. Another big area is electrical power. So we're in an age now where power conversions are very important. So by power conversions, I mean converting things like wind and hydro, converting that to electricity. So wind turbines run on a concept called the Faraday's law of induction, where a rotating element generates an electric current. So that conversion from motion to electricity is a fundamental concept in electromagnetics. Going the other direction, going from electrical power to motion, that's an electric motor. All right, and now more than ever, electric motors have become important, and they're being used in the most recent vehicles. Tesla, the Volt is a hybrid device. Almost every major car manufacturer has electric vehicles, and I've been hearing things that I think in Germany they're going to be going purely electric within 20, 30 years. Pretty amazing, yeah. It's a very ambitious goal, but they would like to all their vehicles to be electric by right now it's almost 2020. So by 2050, I think they were hoping to do that. Yes. Yes, please. So the question was, will we be purely electric like Germany? Right. There are a lot of political factors. I wish I had the answer to that question. There's a lot of factors that would go into something like that. There's obviously political pressures. You mentioned that the oil and gas is subsidized heavily, and you know, if it weren't for some subsidies, it would be difficult to get some of the renewables off the ground. You know, initially we had a lot of subsidies for solar and wind. That's what helped get these industries off the ground. But the idea was that the subsidies are just an initial crutch. Once these industries grow enough, the more an industry grows, the costs end up coming down. You know, the economies of scale bring some of the costs down, and so then the industry can grow on its own. You know, so the subsidies, of course, have helped, but now it's getting to the point where, you know, you can do the math on these things, and wind has become extremely cheap now. That's why you see wind turbines everywhere. So the economics of it actually will tell you that the wind and solar will actually end up being less expensive than coal and gas in the long run, because they're renewable. It's just that there's a high initial cost associated with it. But once these industries grow to the point where the initial costs are driven down, then that argument, you know, that aspect of it is also gets better, right? But companies in Europe, there's more subsidies for these kinds of things, so that's why some of these renewables have been adopted quicker in those areas, and they're being more ambitious with their goals. Yeah. Mm-hmm. Interesting. I didn't know about that. Thanks for sharing that. So the deregulation of electricity, so any company can generate power and sell it back to the grid. Interesting. Mm-hmm. Mm-hmm. Right. Mm-hmm. Right. Right. Mm-hmm. Yeah, we have gas stations on every corner, right? We don't have the infrastructure. We don't have the same infrastructure for doing vehicle charging. But one of the things that Tesla is trying to do is they're trying to put the chargers in every home, so that you won't need those external charges. So charging having charging components in people's homes, in parking lots where the cars will be parked for long periods of time. Wayne State has a bunch of electrical charging ports now, so I think that's exactly. Exactly. There's a big investment that has to be made. Right, but these things happen.
There's a proposal to do satellite tolling on roads.
Mm.
Every vehicle pays kind of like a Segway, a subway,
Mm-hmm.
and they can drive your phone there now,
Mm-hmm.
trying to get to the technology where you can charge your car.
Wireless driving. Wow, that's interesting.
Just use the for your travel and how much you can charge.
Fantastic. That's a really interesting idea. So, well, the concept of wireless charging, that's just rooted in inductance. So another example of electromagnetics playing a big role now. It's an interesting area to be in. Let me mention a few other things. Electrical systems and appliances. Obviously, anything you plug into the wall runs on electricity. Computers. Computers use electric fields to do computations. consumer electronics, you all use medical devices, medical instruments. Medical imaging is based a lot on the propagation of electromagnetic fields. Have any of you had the X-ray, MRI, any type of imaging done? Those are all electromagnetic fields that are going through your body, and they're being detected on the other end. And so they are somehow being used to generate an image. An MRI, like fields going through your body and just being detected on the other end, that's an X-ray. MRI is significantly more complicated than that. It uses a massive magnet, and there's ways that you can basically generate these magnetic fields, and they interact with your body, and then they give off other electromagnetic fields, and those are detected. It's a very complicated. Even people who study MRI full time still consider it a bit of a black art. But these are all these imaging modalities are based on electromagnetic fields. It's very important to understand that if you ever want to get into that area. This slide is about imaging, so I thought I'd share that with you. PET stands for positron emission tomography. CT is a way to do X-ray tomography, MRI, basic X-rays, and then ultrasound is not exactly an electromagnetics technique, but the other ones are. So these are some very interesting images from the Harvard Neuroimaging Center. It's a technique called fMRI, functional magnetic resonance imaging. And what it allows you to do, it allows you to measure blood flow to different parts of the brain. So whatever parts of your brain are working harder, those areas get more blood. So by measuring blood flow in the brain, they can actually see which areas of your brain light up or are working hard for certain tasks. So if I'm thinking about playing tennis, for example, a certain area of my brain will light up. If I'm thinking about driving a car, other parts of my brain will light up. If I'm happy, certain parts will light up. If I'm sad, I have surprise, and so on. All right, so magnetic resonance imaging uses electromagnetic fields and their interactions with contrast agents that you can put into the brain to actually develop three-dimensional images of the brain, and the areas that are getting more blood flow actually light up. It's really a revolutionary technique to study the brain. And then, of course, many of you have had regular MRIs before to look at bones or look at certain organs, diagnostics, and things like that. We'll be talking about Maxwell's equations, which describes how an electromagnetic wave propagates. And this is just an animation that shows the electric fields and magnetic fields that are involved in electromagnetic waves. It's called an electromagnetic wave, an EM wave, because there's an electric field and a magnetic field. And it turns out that the two are orthogonal to each other. So you can see here that the electric field is pointed in one direction and the magnetic field is pointed 90 degrees from that. So the electric fields I mentioned, the electric and magnetic fields are coupled to each other. So the electric fields, when the electric field reaches a maximum, the magnetic field it reaches a minimum, and so on. They're always orthogonal to each other. And these two fields, the electric fields and the magnetic fields, they propagate in a direction that's orthogonal to both. Okay, we'll talk more about this later. I just want to mention what these waves actually look like. So tall arrow means you have a large electric field. Small arrow means you have a small electric field. So these periods of high, if I'm standing at a point and this electromagnetic wave is propagating this way, at a certain point, the electric field would increase and decrease, increase and decrease. Very much like the ocean. An ocean wave, you'll have a high level of water, low level of water. So in an electromagnetic wave, if you're standing at one point, you'll see high electric field, low electric field, high electric field, low electric field. It'll oscillate. And similar things with the magnetic field. So this wave propagation is obviously very important because we use it for things like imaging, as I showed you on the last slide. We also use it for wireless communication. We can send information on electromagnetic waves because we can encode that into the field intensity. we do digital communication, so we have zeros and ones. So by changing the strength of the electromagnetic field over time, we can send packets of information. You can spend several semesters learning about these coding techniques and ways that we can communicate using wireless communication. So that's not the topic of this class, I'm just mentioning it. Here's another chart that shows the electromagnetic spectrum. Many of you have already learned about this in your physics classes. It's nice to just cover it again. These electromagnetic waves have a property, has a wavelength associated with it. The wavelength is the distance between crest to crest or trough to trough. So it's the length of one of these, a single period of the wave, right? So where my mouse is right here to here. So that's one wavelength. And also these waves have a certain frequency associated with them. If I'm standing at this point in space where my mouse is right now, how many of these waves, how many periods of these waves go by that point per unit time? That's the frequency of the electromagnetic wave. What's that? Is it a sine function? Is the wave a sine function? Yes. Yeah, sine and cosine function. Now, different parts of the, you can imagine that these electromagnetic waves, some have a high frequency, some have a low frequency. Some have a high wavelength, some have a low wavelength. Frequency and wavelength are related to each other. They're inversely related. High frequency generally is low wavelength, and low frequency means a larger wavelength. And so if you look at this chart of the electromagnetic spectrum, you will see the very high frequency radiation, high frequency electromagnetic waves is on this side of the chart, and the low frequency electromagnetic radiation is on this side of the chart. And you can see that the electromagnetic waves are used for so many different things. There's so many different types of electromagnetic energy, and it's all determined by the wavelength and the frequency of that electromagnetic radiation. If we start on this side of the chart, the frequency is in the 10 to the 5th range, so 100 kilohertz or up to a megahertz. These types of waves are used in radios. The typical wavelength is 100 meters or even up to a kilometer, right? Very, very large wavelengths. And those types of waves are very good at propagating through walls, so it's good for radio communication. If we go from the 1 megahertz frequency to the 1 gigahertz frequency, now you're getting into microwave radiation. So these frequencies are used in our mobile phones. Your typical Bluetooth, your typical CDMA, GSM, they're running at maybe 2 gigahertz. It's pretty typical. 900 megahertz to 2 gigahertz is what your cell phones operate at. Wi-Fi signals in your house, that's around 2.4 gigahertz. When you go beyond the 2 gigahertz range and you get into the 1 to 100 gigahertz range, you're talking about different types of radar that's used in military applications or satellite communications. Now, once you get to even higher frequencies, now this is an area of research right now. This is the terahertz part of the spectrum. So the terahertz means that you're working at 10 to the 12th hertz. It's more difficult to generate terahertz radiation, more difficult to detect terahertz radiation than it is to work at these lower frequencies. They call this the terahertz gap, and there's a lot of research in this area because terahertz radiation can be used for imaging, it can be used for screening, and there's many other applications on it. Some of you have maybe heard about metamaterials and things like that. One of the faculty members in our department works in this area, terahertz imaging. Moving on, once you get into higher frequencies, then you're getting into visible light. So infrared, visible light, and ultraviolet light. So now you're getting into basically different frequencies of light. This is all electromagnetic radiation. Some of the electromagnetic radiation we can see as light, and some of them are invisible. But they're all basically the same electric and magnetic waves. It's just different frequencies or wavelengths. So within the optical region, which is in 10 to the 13 hertz all the way up to 10 to the 16th hertz, you start out with infrared radiation, then visible light, then ultraviolet radiation. And visible light, obviously, our light bulbs are used there. Ultraviolet light is a light that comes from the sun. Infrared light, if you ever stand under one of those heaters, some of these restaurants have these lamps that emit heat from them. That's infrared radiation. Your TV remote, that's infrared radiation. Once you start getting into higher frequencies, that means that higher frequencies are higher energy. Then those types of waves can be used for other applications. For example, X-rays are in the 10 to the 19th hertz, and their typical wavelengths are in the 10 to the negative 10 meters. So that's used for medical imaging and baggage screening and something called crystallography. And by the time you get to here, 10 to the 20th, 10 to the 21 hertz, this is gamma radiation, very high energy radiation, small wavelengths, high frequency. These are often emitted from astronomical objects. There are some types of gamma radiation which is used in PET imaging. So in general, by the way, the higher you go up in energy, or the higher the frequency, the more dangerous it is to you. All right, so you could be exposed to radio waves, visible light. Once you start getting into ultraviolet, that can be harmful. So ultraviolet rays from the sun, X-rays. You don't want to spend too much time under an X-ray machine. It's just enough to get the image, and then you're out of there. You definitely don't want to be exposed to gamma radiation. The higher the energy, the more danger it is to your DNA. You can get mutations in your DNA, and all sorts of bad stuff happens from there. Yeah.
What was the difference between PET imaging and
fMRI, that's a good question. What's the difference between PET imaging and fMRI? It's the type of radiation that's used, the frequency and the wavelength of the radiation that's used. I believe MRI uses radiation in the, this is a good question. I believe in the microwave range, and then PET imaging uses high energy radiation. They work in fundamentally different ways. PET imaging, I'm not as familiar with, but you could do a Google search on it. It has to do with. Oh, please go ahead. And there's a big detector that detects when those positrons are being given off, and it can locate the exact position in your body where that was given off, and so it can be used to do three-dimensional imaging. It's very interesting, yeah. I'm not an expert in the PET area. So thank you for your input there. Appreciate it. But if you're interested in biomedical imaging, I can point you to some references to learn more about it. I think for the purposes of this class, you just know that like the interaction of the electromagnetic fields within your body actually can be used for imaging. So I think we're out of time today. So we'll talk about, we'll continue this conversation next week. We'll spend the first maybe 15, 20 minutes of class talking about more applications of electromagnetics, and then we'll immediately jump into review of vector calculus. So please leave the white sheets of paper that you filled out. Leave them up here so I have, I can remember your name and know where you're, learn a little bit about you. And if you have any questions, let me know. Next week we'll have no class on Monday. We'll see you next Wednesday.
Just one question. So the thing,